morning. My name is Aric Olson, the president of Jain Irrigation. I'm happy to be here this morning to be speaking about innovation and entrepreneurship in ag and water management. I want to thank the Water for Food organization for putting on this amazing conference. You always do an incredible job. The title of my presentation is called The Renaissance of Irrigated Agriculture. Why Renaissance? It's really because we have this amazing irrigation equipment that's been out for many, many years. Center pivots have been in deployment and improvement over 70 years now, and drip irrigation's been installed for a little over 60 years. Our own Dick Chapin, who invented drip tape, invented that in the 1960s. And he'd be pretty proud of this picture on the right where you can see a drip irrigated field perfectly watering and irrigating, fertigating this vegetable crop in a very uniform row where little or no water waste or fertilizer waste. In addition, we have low-cost, reliable sensors, connectivity and compute power and speed. We've got these amazing machine learning tools, and there's plenty of very good satellite tools that provide daily images for us and allow us to do calculations such as vigor and ET. We also have very good and low-cost control applications, so we can take all these inputs to control our irrigation systems, all backed by very good science about how to precisely tell us when and how to water irrigation or water our crops. And this leads to smart irrigation systems or smart autonomous irrigation systems. To demonstrate and show you the capability of what actually exists, I'll play this little video for you that shows the Jain Genesys in action. We've been working on this smart sprinkler, the Jain Genesys, for more than 10 years. And as you look across the span of this center pivot, you can see variable rate in action. Each sprinkler is capable of watering at its own rate from 0 to 22 gallons per minute. It can have a throw distance of 7 to 25 feet, and it can also change the droplet size by changing the revolution. The power to control this sprinkler in its onboard chipset all comes from the water pressure going directly into the sprinkler. This is definitely a product of the future. Before we talk about more futuristic products and applications, I want to take a minute to step back in time and how people would traditionally irrigate today. Today, most people are irrigating by looking at the crop needs and or the soil water bank and thinking about replenishing that. Many of us in the USA are looking at the ETC, the evapotranspiration rate of the crop, and looking at least replacing the ETC for yesterday or the week. The table on the right shows a calculation of how we determine how much water to apply. Typically, we'll take a daily ETO, which is a well-watered turf grass, and we multiply it by a crop coefficient for that crop you're growing. You can then multiply it by an environmental factor and get a daily ETC for your crop. We would then divide it by the application rate of your sprinkler or drip set, and then that application rate is further divided by the distribution uniformity to get you the forecasted hours of applying water. Now, what happens if any of these assessments are off? What if your ETC calculation is off by 10%? What if the application rate is not working properly and is off by 10%? If you overestimate your ETC, you underestimate your DU, and you underestimate your application rate, and if you do that each by 10%, rather than watering 35 hours to just replace the ETC for the week, you would need to irrigate. That schedule would come out at 49 hours or almost 30% more watering. So it's very important that while we have all these amazing technologies, to get the simplest equations and to make sure we're accurate. Know your application rate, know your DU, and know your ETC. Get the best ETC measurement that you can. These factors are all critical for not wasting water. You've heard the statistics that 70 or 80% of the consumptive water use that we have in society today goes to agriculture. And you've heard statistics that 20% of the irrigated or cultivated land produces 40% of the total food produced worldwide. That's irrigated. In the U.S., there's 58 million acres of irrigated farmland that puts an average of 1.5 acre feet. And that total consumptive water use for agriculture is 28 trillion gallons. Just to put this in perspective, the size of, or the amount of water in Lake Tahoe is about 37 trillion gallons. And Lake Tahoe is a large freshwater lake that's about 1,600 feet deep on the California-Nevada border. And so every year we're using about 3/4 of Lake Tahoe's water for irrigated agriculture in America. So the calculations I just went through, if we could save 10% of that water, you know, that's nearly 3 trillion gallons of water that we could save. So consider the source of these numbers, the potential error of the numbers, make sure we're getting the measurements. And I would also highlight that you should look at these numbers daily. The numbers there on the bottom for forecast hours for running your irrigation system vary greatly in 1 week. I'm going from 7.3 hours on the 27th to the last day on this calendar here to 4.8 hours. It's a huge change. So if you're simply irrigating 6 hours every day, you're over or under irrigating on many of the days. So it's very important to save this water, this 3 trillion gallons of potential savings if we save 10% of the water. We have the tools to do it. And if we irrigate perfectly, we're going to get maximum yield for the crop. We're going to make maximum profit potential. And probably just as importantly, we're going to eliminate waste. There's a significant amount of waste that occurs in evaporation in irrigation. Every one of us has seen a center pivot or sprinkler system running at 100-degree heat with 20% relative humidity with a 30-mile-an-hour wind. Maybe only half of that water is getting to the ground and to the roots. Half of that water is going straight up to the cloud or to the atmosphere. That is wasted water, energy, and doesn't help the crop grow. There's also elimination of runoff and deep percolation if we get the right amount of water applied. There's going to be less environmental fouling because nitrates move with water through the groundwater. So we would have less nitrates in the groundwater and in the waterways. And we'll also be using less energy overall with this water savings. So let's get it perfect. The good news is we have this amazing technology to help us do so. We have soil moisture probes that allow us to get the timing and duration of the irrigation events properly. That last example where I showed 36 hours per week, if you applied all 36 hours in the first day and a half of the week, most likely you would over-apply or push water and nitrates past the root zone of the crop. So soil moisture probes look at where your root zone is and help you get the timing and duration of each irrigation event because water moves through the soil differently for sand versus clay, silt, or loams. The soil moisture probes are pretty amazing to help you set the schedule. Local weather stations and weather networks are perfect for getting that honed-in ETC calculation are important for that. There are very expensive ET measurement devices, and there's very good weather networks to help get good ET measurements in the U.S. and other places. We have variable rate technology. I gave you an example of the Jain Genesys. There's other variable rate technology in center pivots and drift that can help us apply water and fertilizer on these large blocks where we have soil changes, crop canopy changes, or we simply want to turn off water or irrigate more heavily. And we have this two-way communication that allow us to not only monitor the crop, but also provide control applications for turning water on. Now, that sounds great, but there have been significant challenges in getting ag tech adopted. The agriculture industry has been known as one of the least digitized industries out there, and it is so for various reasons. One, we've maybe had a lot of startups offering products or solutions that were not fully ready to be commercialized and maybe didn't have some success. That led us to show the farmer or prove that the new technology actually will work this time. There are challenges with grower density. If you drive in the Central Valley of California, you have access to a lot of large farms, and it's a little bit easier to sell and service the ag technology. If you're in different rural parts of Kansas or Oklahoma, it's a little bit more difficult. You have to drive pretty far distances to be able to get the same level of grower access. So that grower-farmer density has been an issue. Probably the main culprit on why ag tech has not been adopted much faster than it has in other industries is that the training and level of support given to the growers has not been good, and it's not satisfactory, and oftentimes many widgets are being sold as the solution for the grower, but these tools are dropped off with the farmer or installed, and then the service company or product company will walk away, and then there's little or no follow-up or training. And one of the biggest issues is the growers have a lot of risk, and they get one crop per season in many cases. And so under that scenario, the grower's taking a lot of the risk on. And so in those scenarios, they would do very small trials over numerous years, so it takes them much longer to get ag tech adoption because of the geography and the timing of the number of testing that you can actually get done. Well, some really pretty positive and bright news. Just this last week, Landsat launched, NASA launched a Landsat 9 satellite. That's the picture on the left just a week ago. And the picture at the bottom is what the Landsat 9 satellite will actually look like. The picture on the right is a photo of Landsat 8 that's been in operation for quite a while. We have over 8,000 satellites that have been launched since 1957. And it's pretty amazing what these satellite tools can do for us in agriculture, and as far as measuring water use, land use, fertilizer, soil moisture, yield predictions, and things like that. These tools have been in place again since 1957. The drawback of satellites in the past had been they don't work in cloudy areas, so it's maybe fine in the Central Valley of California where there's less cloud cover, but maybe in different parts of the country, Florida, where there's clouds every day, the satellites come over once a week and you miss it, so that's been a drawback of satellites, but that's now changing. It's been changed with the combination of the Landsat program with Sentinel-2. You can get revisit rates in the 5 to 7 day period. And you get resolution. That's also been a drawback of satellites, down to 30 meters. Now that's pretty good when you look at the agriculture area that you can really impact the change with water. Many people won't irrigate in a zone less than 30 meters, so 30-meter resolution has been pretty fine till now. On the private side, we have companies such as Planet, who claim to have more than 200 satellites in lower orbit with the capability to give you images of the crops and fields, of daily revisit rates, and they got resolution that can get to in the 3 to 5 meter range and also down to the 0.8. So pretty exciting what this will help us do in agriculture to monitor our crops, monitor our soil moisture, help us provide variable rate programs for our irrigation tool sets. Now, we've been fortunate enough to use this satellite imagery to help create irrigation schedules and gathering data as far as ETC, actual potential ETC calculations, along with vigor. And we use that as a tool along with our soil moisture tools to help us determine when and how long to irrigate. We're also combining that with the local weather data and local weather stations. And we're using this in a unique format along with machine learning on our soil moisture data to give a very precise irrigation schedule. So we hope to minimize or eliminate over-irrigating, irrigating past the root zone. And these tools are all required to help you do that. There isn't one tool that I believe that can do all what a soil moisture sensor weather station along with the satellite imagery that can do in a way. Now, pretty complex to take a satellite image, a weather station, soil moisture sensor to create an irrigation schedule. Many people sell these as one-off solutions, and we've brought this all together under a brand called Jain Logic to give growers weekly irrigation schedules, how much to irrigate each day based on either forward-looking weather forecast or a replenishment method using the satellite moisture, and then using that soil moisture sensor to tell you when and how to irrigate each day. Now, it's pretty complex, so we've combined all of these tools, or brought these together in providing these irrigation schedules for the grower in a service program called Jain Water Management Services. And this is, I think, really critical because this technology is complex and it's not easy to use or understand. And you also need to have a good understanding of the irrigation systems and how they work. You have to have a good understanding of the agronomy and the agronomic aspects of many different crops, permanent or commodity crops. So this training component, I think, is absolutely critical to have success for ag tech. You could have the greatest technology, but if you just drop it off and you don't help the growers utilize it, it won't take off. So we've had very good success in this Jain Water Management Service program. It's a complete offering. We can do monitoring and control, and we provide all these agronomic insights. The partnerships are very important. We have a partnership with AgroLogics. We have flexible pricing, hardware, software, so I think those are important. But that training and support is probably the most important aspect of deploying ag technology. So I think the future is now, with the climate impacts and labor challenges, we have these solutions for autonomous irrigation. We're doing autonomous irrigation in commercial landscapes today. We have over 10,000 commercial landscape sites that are using the Penman-Monteith ET equation, sending an irrigation program daily to the irrigation controller and adjusting irrigation based on the weather and the forecast and the soil moisture balance. So pretty amazing technology. We're doing autonomous irrigation today. For ag, there's a few more inputs that we will be making. That inputs is that satellite imagery and the soil moisture sensing. And bringing that all together and using the machine learning tools gives us autonomous irrigation in ag. Sending that schedule to the Jain Genesys is going to be pretty amazing, or our variable rate drip system. We'll be able to use that with closed loop feedback. So that sounds good, but how do we prove this out? How do we get this technology to the grower? How can the grower have confidence that this technology has been properly vetted? I think a key way, and I want to put a plug in for the Irrigation Innovation Consortium, and this organization focuses on doing pre-competitive research, white space research in irrigated agriculture. And it was founded by a grant from FAR and the USDA with these 5 main universities there listed on the top of the picture there, with a few founding companies. And they're doing amazing research over the last 3 and 4 years. And I encourage you to look up the Irrigation Innovation Consortium. if you're a company with really amazing technology and you want to find a partner or a way to vet or test the technology, please get a hold of the Irrigation Innovation Consortium. If you want to trial something and be part of the research, there's research grant money that can be available as well. So in summary, we're really in a renaissance period for irrigated agriculture. We have amazing equipment. There's low-cost, two-way communication. We have this technology and tools available. There's plentiful satellites with good revisit rates and resolution. We are doing smart autonomous irrigation today in landscape. This is coming to agriculture because we've added this satellite capability. As a result, we're going to get better crops, more value for the grower, less falling of the environment, and it's better for the planet while feeding the population. So with that, I wanted to thank you for your time. I hope you enjoy the rest of the 2021 Water for Food Conference. My name is Aric Olson. My email contact is below. Thanks again.